Welcome to the 11th webinar in Contact's Produce Safety webinar series. This second season will tackle a new fresh produce safety topic every month through a dynamic webinar series that will bring together industry, academia, and regulatory minds to solve some of the produce industry's biggest and most timely challenges. This series is part of a larger industry outreach and risk mitigation project called Contact, or scientific challenges and cost-effective management of risks associated with implementation of produce safety regulations. This project is supported by the Specialty Crops Research Initiative from the USDA National Institute of Food and Agriculture. Any opinions, findings, conclusions, or recommendations expressed in this presentation are those of the speakers and do not necessarily reflect the view of the U.S. Department of Agriculture. This webinar series, coupled with other research and extension efforts, is part of a collaborative effort across 10 different universities and government institutions to enhance produce safety knowledge and compliance across the industry. We are so grateful to our collaborators for their efforts and support of this webinar series. You can see the logos on the screen. The webinar series will continue next month with a panel of experts discussing data sharing. Sonia Salas will lead the presentation series, and Dr. Emily from the International Fresh Produce Association will moderate the Q&A session to follow, and this will occur on Thursday, January 12th, 2023. Our catchy new title, The Future is Now, How Data Sharing Enhances Food Safety. We all hope you can join us. This year's webinar series will address brand new topics chosen by you. We've got an exciting new list of webinars scheduled for this year, covering topics like sanitation, foodborne outbreak, attribution, and more. If you think a topic is missing from this list, let us know in the comments, webinar surveys, or on our social media pages. While the webinar series lets us meet with you once a month, you know what I'm going to say. We just love to hashtag make contact with you. We want to make contact with you about today's webinar or other produce safety news and research on our Twitter and Instagram pages. Follow us on these platforms at PS_Sci, SCI. Additionally, check out Contact's YouTube page. This is a great new resource. It's got the 1-hour content of these webinars, our key takeaway documents that give an elevated synopsis of the webinars. It also features our clarifying the confusing content, a fun segment. Can you clarify something that's confusing in 90 seconds? Again, we challenge you. Please let us know if you want to participate. You can open Google, type Produce Safety Science, YouTube, and it'll pop up. You can also find these links on the slide, or go to the Contact website homepage, click on the drop-down menu and select Resources. A quick reminder for today, if you would like to submit a question for our speaker during or before the Q&A session, please submit your questions through the Q&A box and not the chat box. Now, let's welcome our speaker. Dr. Donald W. Schaffner is an extension specialist in food science and a distinguished professor at Rutgers University. His research interests include hand washing, cross-contamination, and qualitative microbial risk assessment. He has authored more than 195 peer-reviewed publications and educated thousands of food safety and food industry professionals around the world. He is a fellow of the Institute of Food Technologists, the American Academy of Microbiology, and International Association for Food Protection, IAFP. He served as the editor for the ASM journal Applied and Environmental Microbiology from 2005 to 2020. He began serving as a contributing editor for the journal Food Microbiology and an associate editor for comprehensive reviews in food science and food safety in 2020. Dr. Schaffner was the president of IAFP in 2013 to 2014. In his spare time, he co-hosts the Food Safety Talk and Risky or Not podcasts. Welcome, Don. The floor is yours, and we are so grateful to have you for a second time.
So thank you so much, Laura. So I have the unenviable task of following an excellent presentation last month from Chana Rock. So this is agricultural water. Does this look risky to you? Part 2. So I'm going to build on hopefully what Chana presented, and I'm going to offer maybe some different perspectives on some things that she presented as well. And just because I'm a quantitative guy, one of the things that I did in preparing for this talk is I compared Chana's presentation to mine. And you'll see part 1 in blue, that's how many slides that Chana used. I've got about half as many slides. And also I wanted to compare the physical size of the files. And you can see there that her PowerPoint presentation was over 250 megabytes. The size of my presentation is actually graphed on this graph. You just can't see it because it's about half a megabyte. And so what that means that you're in store for is a whole lot of boring black and white slides, no equations and not too many numbers, but not nearly as many cool pictures as Chana had. So I hope you'll still find it enjoyable and informative. What I'm going to talk about today, I'm going to open with an introduction to microbial risk assessment. And I'm going to talk about key differences between risk assessment and risk management. And I'm also going to talk about the difference between hazard and risk. And again, these are topics that Chana covered before, but I'm going to cover them again with my perspective. One of the things that you may remember from Chana's presentation last month was she used severity and probability matrices. I want to spend a little bit of time with you today talking about severity and probability matrices, but also hopefully pointing out for you in a way that I hope is clear what some of the pitfalls of using these matrices. I want to talk about a couple of different ways of viewing risk, specifically the difference between looking at risk per serving and looking at a population risk. And then I want to talk about an example that I pulled from a related example from another talk about what the risk would be from meeting a standard versus not meeting a standard. And then finally, I'm going to conclude with some thoughts on the FDA Ag Water assessment. So let's get into it. Risk analysis is commonly thought of as having 3 components. And you may also hear the word risk analysis used interchangeably with, or the phrase risk analysis used interchangeably with the phrase risk assessment. And in fact, they do mean different things. They mean different things to risk analysts. They mean different things to risk assessors. So I am using the conventional definition here, which is that risk analysis is the entire field and risk assessment is a component of risk analysis. Kind of risk assessment that I like to talk about is quantitative risk assessment. Now, those probability matrices that we're going to talk about in a little bit, they're semi-quantitative or maybe not quantitative. Maybe they're qualitative risk assessments, but I like to focus on the quantitative aspects of risk assessment. And so if you're doing a quantitative risk assessment, it's really answering the question, how big is the risk? And also, hopefully, what factors control that risk? And if we know the size of the risk and we know the factors that control the risk, that hopefully gives us some levers or dials that we can turn to cause that risk to go down. I would describe risk assessment as a scientific process. It's driven by data from the scientific literature or from other high quality data sets. It uses math and statistics to build these computer models that allow us to assess risk. Second component of risk analysis is something called risk communication. Risk communication is really talking about risk with the affected individuals. So in this particular case, it might be talking with the food industry about how they might manage risk or how they might assess risk. It might also mean talking to consumers who are worried about a particular risk of something or other. There are dedicated scientists out there who, and I'm not one of them, who study how to effectively communicate about risk. And the people that study risk communication, they are psychologists or they are social scientists. So I am neither of those things, but I do spend a fair bit of time talking about risk to people that are affected by that risk. I guess you could call me a risk communicator, but I'm not trained as a risk communicator. It's just something that I do as part of my job. The third component of risk analysis is risk management. And risk management deals with what, now that we have this risk assessment, or now that we know that we have this risk, what do we actually do about it? I would say most of you folks here on the call, if you're at an academic institution, maybe you work on risk assessment or you work on data for risk assessment. If you work in the food industry, you are probably some sort of a risk manager. That is, it's your job to decide what to do about a particular risk. Risk management is not a scientific process. It should hopefully be informed by science and informed by the scientific process, but I would characterize it as a political process, and we're political not as in political parties, but it's really a management process, and it's not science. It really is dealing with trade-offs that are not always able to be expressed quantitatively. And so that if you don't take anything else away from my talk, take away that thought that a risk assessment should never tell a risk manager what to do. The risk assessment should lay out for the manager what the options are, and then it's up to the manager, who typically is paid way more than the risk assessor, to make a decision about what to actually do about that risk. Okay. So again, let's open now, or let's follow with some definitions. And again, these are definitions I believe that Chana shared last month, but I think they're worth revisiting. So the first take-home message is risk assessment is different than risk management. The second take-home message is that hazard is not the same as risk, okay? A hazard is a biological, chemical, or a physical agent in or condition of food, which has the potential to cause an adverse health effect. That's not my definition. I think that is the Codex definition. So it's a little bit wordy, but again, what are the key aspects of this? Typically, if we're talking about fresh produce and food safety, we're probably mostly talking about microbiological risk, which would fall into the biological category. But if we're thinking about HACCP, hazard analysis and critical control points to food safety, we may also be worried about chemicals. So excess concentrations of sanitizers or elevated levels of pesticides. Or we may also talk about physical agents. That would be a splinter or a rock, metal fragment, something that is physically present in food that we don't expect to be there, such that when we bite down on it, we'll get an injury in our mouth or we'll chip a tooth or something like that. Risk is very different. Risk basically deals with the probability of an adverse health effect and the severity of that effect consequential to a hazard in food. So if we have a hazard in food, if we want to manage that hazard appropriately, we need to understand the probability that the hazard will be there, and then also what's going to happen when someone is exposed to that hazard. My reaction to a dose of salmonella is going to be different than my reaction to finding a stone or a rock, biting down into a stone or a rock in the food. One is probably potentially much more significant, especially if I get infected and I get sick from the salmonella. Certainly biting down on a rock is not pleasant, but it probably just means a trip to the dentist. So I use that example to illustrate the differences in severity that we might see. Okay. I alluded to this already, but let me go back and reemphasize. So a hazard is something like salmonella, Listeria monocytogenes, pesticide residue. And with hazard-based thinking was good. It got us pretty far in terms of food safety. But basically what hazard-based thinking says is hazard bad, don't have it in food. And so we all know, I think we can all agree here today, that we shouldn't have salmonella in our food. We shouldn't have Listeria monocytogenes in our food. We should not have elevated pesticide levels in our food. I think it's a statement we can all agree with, but it's not necessarily really helpful if it comes down to what do we do to manage this risk. Like I said, risk deals with probability and severity, and I've got a whole lot of text here talking about the fraction of servings that are contaminated and the chances of diarrhea and the chance of hospitalization and the chance of death. And I've used this slide for a long time. I don't particularly like it because I think when I start rattling through those numbers, what it sounds like to many of you is just blah, blah, blah. Schaffner's talking about numbers. Okay, we get it. Numbers are important. But honestly, even to me, looking at those numbers, that's not really helpful in terms of what do we do about managing risk. All right, so let's transition to the next phase of what I'm going to present, and that is the severity and probability matrix. And again, this has some intuitive appeal. You saw a bunch of these presented by Chana last month, and basically what it says is, we're going to manage risk, like I just said, and I just already told you that risk is about severity and probability. So let's make a nice, simple diagram that's going to help us understand severity and probability. And we can make a matrix with 2 categories in each dimension. We could make it in 3 in each dimension. We can make it in 5 or 11 or however many we want in each dimension. We can make more dimensions for severity. We could have a 5x3 matrix or a 3x5 matrix, right? So we're really unlimited in terms of our choices here. And again, it has a nice intuitive appeal, right? Because if severity is low and probability is low, then it's low multiplied by low, which, as we all know, is what? Low or really low, right? Again, makes perfect sense. And conversely, if we have high severity, high probability, we've got high multiplied by high, okay? And that gives us a really high number or something, right? And we've also got these other categories, right? Medium severity and low probability, just medium times low. And we've also got low severity, medium probability. And so that's low times medium. And you would think if words behaved like numbers, that medium times low is the same as low times medium. So if you think about this matrix, the idea is we want to be in the lower left-hand corner, and we don't want to be in the upper right-hand corner. And what we should try to do is move from the upper right to the lower left, and we're going to do that by making appropriate risk management decisions. Okay, so now I'm going to explain to you why maybe there's some problems with this approach. So what I've done here is I've taken that same matrix. I'm just going to move this window out of the way here. So I've taken that same matrix that I just showed you, except now instead of using words, which you really cannot multiply together as much as I showed you that you could, and I've converted it to numbers. And so now we've got, again, severity on one axis and probability on the other, and it doesn't really matter. This is an artificial example, so it doesn't matter which is which, and it's not labeled, so I'm probably going to forget which is which at some point, but that's okay. And so again, we have severity, I think it is, going from 1 to 100, and we have probability going from 0.01 to 1. Okay, that makes perfect sense, right? We've got something that's not severe, something that's intermediately severe and more severe, and we've got different probabilities. And so now we just multiply the numbers, right? And so if the severity is 1 and the probability is 0.01, that gives us a score of 0.01, which is a really low number. And so that's good, right? We want risk to be low. Same thing for high multiplied by high. If it's 100 severity and it's a probability of 1, 100 times 1 is 100, and that's bad, right? So you don't want to be at 100 in this case because a higher number is bad. So we want to move from 100 down to 10, down to 1, down to 0.1, down to 0.01. So everything is fine. Also, just by coincidence, because of the way we set this matrix up, medium times low is the same as low times medium, right? So 10 times 0.01 is the same as 1 times 0.1. Everything is great. And the diagonals that we have on the graph are the same, right? And again, medium times low equals low times medium. It's all good, right? So that's the animation I was going to try to get to pull up there. So you can see on the diagonals, everything's fine. Okay, but you sense now I'm setting you up, and indeed I am. What if we, instead of having severity and probability go on the axis, on the numbers that I've given, what if we change them to different numbers? Something is not right now, okay? So now I've changed the numbers on one or more of the axes, okay? And now, and again, this is a simple Excel spreadsheet. If anybody would like a copy of the spreadsheet to play around with, if you don't trust my numbers, you can play around with the Excel spreadsheet. And now what is, some things are still the same, right? Low times low is still really low, and high times high is still really high, right? So now in the upper right-hand corner, you can see we're up to 100, which is the same place we were before. And now I think in the lower left, we're probably down a little bit lower than we used to be. But now in this case, medium times low is equal to low times high. And the diagonals are not the same, right? So you can see those diagonals are not the same. And now it really matters how we decide to place those categories and what bins we want to put our risk in, because now moving along the diagonal actually might give you a different risk. Now, what if we take the same example and we push it a little bit further to the breaking point? Okay. And again, I've now changed the scales a little bit. It's all still, the calculations are all still be done in Excel, right? Again, lower left, still fine. It's the lowest number. Upper right, still fine. It's the highest number. But now there's all sorts of weird stuff that's going on in the middle. Now, high times low is greater than medium times high. In other words, 11.11 is greater than 1, right? So that doesn't really now make too much sense. If the severity is high and the probability is low, we are in a much riskier situation if these numbers are meant to reflect risk than if the severity is medium and the probability is high. So if you were managing risk and the probabilities and the severities corresponded to the numbers that I placed on the edges of this table, you would be severely misled if you wanted to, let's say, if you decided, okay, I know 100 is bad, so what I'm going to really do is I'm going to reduce the probability a whole lot, right? And now my risk has gone from 100 to down to 11 or a little bit more than 11, but that's not the same as moving along the other axis. And so where does this leave us with these matrices? They are certainly appealing because they're simple. And because they're simple and because they don't typically use numbers like I've illustrated here, have an intuitive appeal. But if you try to put some numbers to them, what you'll figure out pretty quickly is that they might be misleading. And boxes that are colored the same color on a matrix might not actually have the same level of risk, depending upon what those words actually mean, or what the numbers are that correspond to the words that you put on the edge of the matrix. Okay, so I want to give you some more examples to think about, just to get your head into this risk space. Let's consider, because this is a talk about ag water, let's consider that we have two agricultural water sources that we're interested in. Let's call them source A and source B. Source A is used to irrigate many acres, and we know from testing data, let's say, or maybe other things, that source A is really very low risk, or it's low risk when it comes to putting onto food crops. Source B, we know that source B is not a very good water source, and we would call it, for the sake of this discussion, let's call it high risk. But the good news is that we don't use source B to irrigate much, right? We just use it to irrigate a few acres. And again, because I like numbers and I want to make this example about numbers, let's say that source A gives us a risk of about 1 in a million per serving. But remember that source A irrigates many acres, and so many servings of this low risk irrigated crop are going to be consumed every year. Source B has a high risk, right? And let's say, again, for the sake of discussion, a risk of 1 in 100 of giving someone food poisoning. But the good news is that we're not irrigating very much with this high risk water. And so that product is only going to be consumed by a few people. So let's go a little further and maybe take these numbers and plug them into some graphs, because that is a much easier way, I think, for us to see what's going on. So what I would ask you is, which is riskier? And it's a trick question, okay? Because again, we've got water source A and water source B. Based on the assumptions that I gave you, water source A is going to generate way more cases of illness every year than water source B. Why is that? It's a low risk water, but we use it on a massive amount of crops which are highly consumed. B, the risk is very high for anything we irrigate with that, but we don't irrigate a whole lot with that. And so the actual, again, these are hypothetical examples, but the number of cases we would expect from source B is much less, not because the risk is less from the water, but because we don't irrigate very much with it. Same exact data, right? But now, instead of looking at the number of expected illnesses, let's think about the risk per serving. So the graph on the left might be from a producer, but the graph on the right is really what the consumer is seeing, right? And what you can see is that the risk per serving, if I have a choice as a consumer, should I choose water irrigated with B or with A, I should absolutely choose food that's irrigated with A, right? Because the risk is much higher per serving for food that's irrigated with source B. And you can see that, right? The risk per serving is 0.01. Like I said before, that's 1 in 100. My risk from water irrigated with source B is much lower. It's only 1 in a million. And so from a consumer perspective, I am absolutely going to choose food that's irrigated with source A. But if I'm the person that's irrigating food with source A and source B, and I've got a lot more servings out there on the market irrigated with source A, that risk is going to be higher for me. Again, there's no magic here. This is a spreadsheet, and it's making calculations from the same exact data, but it's just a different way of viewing it. Okay. So if I haven't completely overwhelmed you with numbers and risk-based thinking, I'm going to move on to another example. Okay. And let's talk about here now about testing criteria. And for the sake of the argument, we don't need to worry about what the criteria are. I'm going to give you some made up criteria. But the question I have for you is, would you worry more about using water that meets the testing criteria only 50% of the time? Or would you worry about water that met the criteria 95% of the time? Now, think about that for a minute. Okay. And if you're paying attention, maybe you're suddenly very suspicious. And if you're all being honest, you're all going to say, I think the 95% is much safer, right? Because it meets the criteria 95% of the time. It's not, and again, it would be, and we could even make an example where it's 99% of the time, right? And everybody would still pick that number. But what I've left out is some really important information, which is how much did you miss hitting the criteria? And let's assume for the sake of discussion that less than 2 log CFU meets the guidelines. 2 log CFU of what, in what volume, doesn't matter. We'll just pick a number, okay? And so we want to be less than 2. Now, what you can see here from this example is that source 1 has a 50% success rate. About 50% of the time, it's less than the guideline. And about 50% of the time, it's just a little bit over the guideline. So did it hit the guideline? No. Is it a problem? Yes. Should we do something about it? Probably the answer is yes. Okay. But contrast that to source number 2, which hits the testing guidelines 95% of the time. But guess what? When source 2 has a defect, it's a massive defect, right? Instead of just missing the criteria, it's way above the criteria. So again, if we're thinking in terms of log CFU, let's say maybe for the sake of discussion, it's 7 log CFU. So much, much riskier. So really, you maybe have changed your answer to say, now I'm much less worried about source 1 and I'm much more worried about source 2. Again, the devil's in the details. It depends upon what's the organism, what are the consequences of that organism, et cetera. But again, what the purpose of this example is to get you to focus on, yes, it's important to hit a specific criterion, but how much away from that criterion, how much you exceed the criterion by might in fact be more important as to whether you actually met it or not. Okay, the time remaining, I just want to talk a little bit about my experiences using the FDA Agricultural Water Assessment Builder. FDA calls this a user-friendly tool. I've put user-friendly in air quotes there. I'm not sure it's as user-friendly as it could be. The purpose of the tool is to help farms understand the proposed requirements. And again, I would mention, so what you can see on the left, that's the text of my slide. On the right is the screenshot from the FDA page that you see when you Google Ag Water Assessment Tool and FDA, and that's what you find. And that text in red at the bottom, that's a big, long legal disclaimer, basically saying that using the builder does not constitute FDA approval or guarantee compliance with the requirements. And their lawyers probably made them put that there. One interesting thing, and when I first heard about the tool, I was calling it a Ag Water Risk Assessment Tool. And I realized as soon as I got a look at the tool that was not correct. If you look on this webpage and you search for the word risk, you don't find it anywhere. If you look at the output from the FDA tool, you also don't see the word risk mentioned anywhere. Again, in an effort to explore the tool and what it it can do. I ran some scenarios and I got some colleagues with more knowledge of ag water than I to fill out some assessments there as well. And so what I want to walk through in these slides is just the different possible outputs that I was able to generate with the tool. And the best possible outcome, if you answer the questions right, is you get an assessment, you get an answer saying, thank you for using the Agricultural Water Assessment Builder. And this basically says covered farms that do not use agricultural water in the growing of covered produce would not be required to prepare a written agricultural water assessment. And the best option you would get is no written assessment needed. There's probably very few agricultural operations that would not use agricultural water in the growing of covered produce. FDA tool output number 2. Again, thank you for using the Ag Water Assessment Builder. You're exempt and no written assessment is needed, but here the text is a little bit different. What it says is if one of these exceptions applies to a covered farm, it would not be required to prepare a written Ag Water Assessment under the proposed rule if finalized. Here is the third option. And in this case, no thank you. There's no thank you given, but the outcome is no hazardous conditions. Based on the information you provided, you have, see, somebody really spent a lot of time on this language. Based on the information that you have provided, you have determined that there are not conditions that are reasonably likely to introduce, et cetera, et cetera. And what the tool then exhorts you to do is to regularly inspect and adequately maintain your agricultural water system, and then assessment annually or whenever you make a significant change. The fourth output that I was able to get from the tool is this one. Again, thank you. Once again, please note the proposed rule would require that covered farms conduct an ag water assessment at least annually or whenever a significant change occurs. And I'll tell you that with each iteration of using the tool, we chose more and more risky behaviors. And so this is the output you'll get under the quote unquote riskiest set of scenarios. And so the previous one said no hazardous conditions. This one doesn't say that you've indicated hazardous conditions, but it doesn't say no hazardous conditions either. I'm sure there's very good reasons why FDA made this tool in the way that they did, but I found it a little bit puzzling and maybe not as helpful as it could. Just a few final thoughts on the FDA tool before I wrap up my remarks. The FDA tool does not assess risk, and it does not claim to assess risk. I think, and again, you folks who think about ag water probably every day may have different opinions on this, but to me, it seems like it's a good start. It's a small start, but a good start to thinking about agricultural water. One thing that is very much a puzzle to me, having spent several hours now playing around with the tool and trying to find all the different outputs that it could generate, it's not clear at all to me how what I put into the tool gives me the outputs that come out of the tool. And if I was going to design a tool like this, I would probably use a spreadsheet, or I would at least provide a diagram that would show how the different parts of the tool are connected to the other parts of the tool. Because for me, I can generate 4 different kinds of outputs. 2 of them are trivial by basically answering questions in a way that indicates that I'm not using agricultural water, but trying to understand how the inputs to the tool lead to the outputs and what I should really do about that is not quite as transparent as it could be. So let me just summarize my remarks and say that I think that risk-based thinking is more useful than hazard-based thinking, right? And I think I'm really pleased to see that we as a food industry have really moved quite far into risk-based thinking. When you practice risk-based thinking, it helps you to focus. And it helps you to clarify your priorities. We know, and again, Jana said this in her remarks, there's no such thing as zero risk. But if we have some sort of a quantitative assessment of risk, we should try to figure out things we can do to bring that risk level down. And hopefully we're doing it in a way that makes mathematical sense and is logical. But again, remember, think back to one of my earlier slides, risk assessment is never going to tell you what to do as a risk manager. As a risk manager, you have to figure out, okay, what can I reasonably achieve? What's it going to cost? Where's most of the risk? And then where are ways that I can mitigate that risk? It might make more sense to mitigate a bunch of medium level risks if they're inexpensive versus a risk that's higher that's going to be really expensive to mitigate. But again, we won't really know that until we get some quantitative assessment of risk. Again, as I said before, risk matrices are seductive because they're simple, and it just seems like all you got to do is look up the severity and look up the probability and then figure out what color the box is, and then you're good to go. But as I hopefully showed you, when you try to put some numbers behind what those matrices are doing, it leads to some situations that are a little bit confusing at best. And I would say the FDA tool is a good start, but it is certainly not a risk-based tool to assess ag water risk. And again, FDA does not claim that it is a risk-based tool. So it would be nice if we had some risk-based tools. I'm also really happy to say that because of the work that we're doing in Contact, maybe at the end of that grant, or maybe in the middle of the grant, we will have some tools that will help us use risk-based thinking and risk-based metrics to assess ag water risk. And with that brings me to my last slide, and I would be happy to take any questions and or have a discussion.
Perfect. Dr. Dawn, I want to thank you. You're always such a pleasure and a good sport, because I did ask you some tough questions, put you on the spot, and I really appreciate that. So thank you again for joining us. I want to remind everyone, we will be sending out a link for January 12th, 2023. So you can kick off the new year, not only with whatever New Year's resolutions you have, but maybe a New Year's resolution to embrace more food safety education. So we'll start to tackle The Future Is Now. You're going to get a couple of different panelists and speakers, so it'll be really fun. So please join us. Thank you so much, and have a wonderful rest of your day, wherever that may be. Thank you again, Dawn.
Thanks, Laura.